Now let us discuss a practical sources. Ideal elements sources exist only in textbooks, not on real circuit board. So we have, till now, we've been discussing only ideal sources, ideal voltage source and ideal current source, and these relationships you have here in green. In practice, we have some internal resistance for both voltage and current source. Then non-ideal, a practical voltage source is this line in black here, and a practical current source also this is a line which is not perpendicular to vertical axis for current source, which is not perpendicular to voltage axis in case of a voltage source. So we may, doesn't matter whether our source is a current source or a voltage source, we may say that our I relationship, it is a line which crosses a voltage axis at E sub O, the open circuit voltage, and current axis at J sub S, short circuit current. Having this line, we may obviously write down equations of this line, and from these equations we may obtain a Thevenin equivalent or Norton equivalent as at the left side here on the slide. So let us conclude. Any practical source, it doesn't matter whether voltage source or current source, can be expressed by Thevenin equivalent or Norton equivalent, which means it is a series connection of a voltage source, an open circuit voltage source, and internal resistance R sub T, or it is a parallel connection of an ideal current source and conductance G sub T. Now let us consider the characteristic U and I, U for voltage source and I for current source, as a function of load resistance. Actually, after normalization of this horizontal axis, it is a ratio of load resistance to internal resistance of our source. So for voltage source, we may find that this voltage is expressed by this equation, which means that okay, we have E sub O for R sub L equal infinity, and we have 0 at 0. So our function actually, it is like that. It is not the green line as it should be for an ideal source. For practical source, it is this line in red, line curve in red. So actually our source operating point should be located somewhere here, where we have quite large ratio of load resistance to internal resistance of the source. And for current source, very similar reasoning, only here for very small ratio R sub L to R sub T, we have already current source. If R sub L is large, then simply we don't have any more current source. I mean source that forces a given current of J sub S through the load. This is condition that should be satisfied for a source, a voltage source or current source, if you want this source to operate as the source has been designed. Now the problem of voltage to current source conversion, a practical problem. We have a voltage source which is easy to find, to build, and then we want a current source. Can we then convert a voltage source to current source? Yes, we can do this very easily. How? So this is our original source, a battery, and obviously this line crosses the current axis at some very large current, but we want a smaller current to be the current of a current source. What can be done? How can we reach this situation? By series connection of resistance in series with our voltage source. And actually this resistance of this resistor should be obviously much larger than R sub T, also much larger than this load resistance. And current which flows in this mesh, in this circuit, actually is limited. Current I is limited is designated by this resistance that we have connected in series. That way we have obtained a current source from our voltage source. This is a relationship after adding this resistance, this series resistance. Unfortunately, this solution is very ineffective, so it is repeated. We have this line moving from this position to this position, or after adding this series resistance. Unfortunately, efficiency, sprawność, efficiency of such system, efficiency defined as power which is absorbed by a load to power which is produced by an ideal source, and efficiency of this circuit for the given values of R sub L and R sub T, which are here. I'm sorry, I think that, sorry, it is just general. It is just general, so it is very small efficiency, less than 10%. For this practical circuit, we have some values of, this is 9-volt battery and 3 ohm internal resistance. Obviously, it can be converted to a current source. And then we may, from this, from this voltage source, we have obtained a current source of 1 milliamp. However, efficiency is 9% only. Okay, I think that we will discuss this issue, this practical source example, at the lecture room, and for now on, that's all. Thank you.